So thank you. It's a great honor for me to present a lecture here to the total community. I'm very glad to be here again. I have attended many conferences of this type, and I will talk about things James would have called K-12 material. Or did you say K212? So I propose a new approximation method for zeros of an algebraic equation. Okay. I think I can keep it. So the method generalizes facts of the usual treatment of the golden mean, and I think everybody knows about this. This is common knowledge. The method is perhaps a nice topic for teachers and to teach in high schools because it combines informatics, it combines mathematics and geometry and many topics you have to teach anyway in schools. And finally, there will be some remarks on mathematic visualization. So the golden ratio, I call it the golden ratio, while the Greeks, the ancient Greeks, in Latin it was sectio aurea, it was the golden section. So the ratio is a signed value. The ratio is a signed value, and we can talk about the ratio of lengths. It's the major to the minor is the same as the total interval of and to the major. It's called phi. Some people are writing tau for this symbol. It is like pi. Everybody knows that phi means this value. So it's the solution of a quadratic equation. Phi squared minus phi minus 1 is 0. And phi is the limit of quotient of consecutive Fibonacci numbers. And the Fibonacci numbers, and there we have again the convention that the first letter of Fibonacci is the letter we use for this symbol. It's defined as the sum of the two previous numbers. And we start, in physics, we start the Fibonacci series with 0 and 1. And in mathematics, we start with 1 and 1. But the limit of the quotient is independent of whatever you take as the start values. For example, you could call it E and pi, and it would work in the same manner. So the limit of the quotient is this 1.618 and so on, independent of these start values. What we have is that this is a solution of a quadratic equation. So I take some things, basic ideas repeated. The positive number phi or tau is either 1.618 or 0.618, and breaking with the traditions, we can call the signed ratio solutions of quadratic equations, both if you want only positive values. It's the extremal continuate fraction, whatever. And we can also take a ratio as an affine concept and embed it in the projective plane or a projective space, enclosed projectively. And then we can talk about the cross ratio. It's a projective geometric invariant, and strange enough, it comes up in some very interesting objects, which are limit figures of hexagons. Limit of Fibonacci number ratio, we will talk about this. There down you see, maybe you see here, you see the continuate fraction. You start with 1 point or with 1 over. And here you have a spiral, which some mathematicians call a logarithmic spiral. This is not the case. This is a biarc spiral. In fact, it's a biarc spiral with C1 continuing, which consists of quarter circles. There you have a natural object, the sunflower, and here is a golden hexagon where this cross ratio occurs. Golden spirals, the quarter circle spiral, and it doesn't depend on squares, of course. You can use any figure, in fact, where the golden ratio occurs to make discrete logarithmic spirals. But geometric knowledge vanished so much that people don't know how to construct touching circles over two segments. This is what we have to do here. Given this segment, and we want to construct a circle over a circular arc over this segment, and a circular arc over this circle, such that these circles suit into the same similarity. And it's just the periphery angle theorem applied twice. The golden mean or golden ratio has to do with limit quotients of Fibonacci sequence, which are later on generalized to Icai and Padoan series. It has to do with paper folding operations, because the golden mean is solution of a quadratic equation. It could be even a solution of a third order equation, such that it could be handled by paper folding. So geometric progression and logarithmic spirals, geometric constructions of higher dimensions, and so on. It's a lot of things which arrived after the golden mean. So, facts about Fibonacci numbers. Usually we have the visualization, putting one square, you see the little ones with 1 and 1 described. So you add the square on the left-hand side 2, and from this order you continue such that you, in some sense, have a circular similarity movement. So what do you really add? You add squares, but you talk about the length of the sides of the squares, and these lengths are the Fibonacci numbers. You have finally a rectangle, and if you add until infinity, this rectangle has a side ratio which is exactly the golden ratio. Squares are the gnomons, as they are called, of this golden rectangle. And here you have again the Fibonacci spiral versus the logarithmic the similarity, the discrete logarithmic spiral on the right-hand side. So you start with this, and I think this Fibonacci spiral is more natural than the other one, the logarithmic part. Because when you compare natural snail houses with logarithmic spirals, you have the conflict of at the pole, there the mathematical object turns infinitely many times around. But the snail starts with cells. And so the Fibonacci spiral is the more natural things. So we have again, all concepts refer also to Euclidean geometry, and Fibonacci numbers are just numbers. They are dimensionless. What do they have to do with Euclidean geometry? So we shall, at the end, discuss some automatic assumptions. We have visualizations of mathematics. So, again, the quadratic equations, both of them, we take only the positive solution. Here belong the Fibonacci sequel, but let us take a general quadratic equation and find a Fibonacci type sequel to those given A and B. And I think this works in the following manner. We start putting just such a Fibonacci type sequel with coefficients p and q, and we calculate by comparing these, we calculate the quadratic equations to it. Then we find fi over fi plus 1, and here fi minus 1, and by calculating this, it turns out that we get p over x and q over x squared. So we find p is a and q is b. So we have found a Fibonacci type sequel such that we get a positive solution of this quadratic equation if there is a solution. Note that quotient sequence is, we have to talk about the convergence, of course, of this series, is the convergence is connected with the equation has real solutions. So, of course, I mean, to solve the quadratic equations approximatively is not a great deal we want to have. But let's start with cubic equations, solving cubic equations, and we can start in the same manner. We take coefficients a, b, c of the equation, and wait a minute. We start with the sequel defined now by 3 neighboring Fibonacci type numbers and coefficients p, q, r, and we make the same calculation, and we find that p is minus a, and so on and so on. You see, it's quite easy to do it with higher order equations too. But we have the problem, it looks like a cubic equations always have a real solution. Yes, it has always a real solution. But in fact, we want to have a Fibonacci type sequel. And for example, the cubic equation x to the third is equal to 2 is a cubic equation. But the coefficients p and q would be 0, and we only have r, and this doesn't give a Fibonacci type sequel. So it's not, we cannot really solve any equations. What can we do? If it's not a Fibonacci type sequel like we have it here and in that manner, the idea is to take the inverse of a Tschirnhaus-Bring-Ferrar transformation. Tschirnhaus, a Dresden guy in about the 17th, he died 1708, and it's long ago, 300 years, more than 300 years ago. He thought that he can make 2 coefficients of an algebraic equations to vanish. And this is somehow true. Here, it was later on proved by Bring and Ferrar, and this transformation is called Bring-Ferrar Tschirnhaus transformations. So if we take this and make it reverse, we find an equation which has all coefficients not 0, and then we have the solution, and we can solve such an equation too. But we have to remember this is the possible way. So you see, here is the Bring-Tschirnhaus transformation if we have a general equation of nth order. So it's always possible to transform it in a polynomial where these 2 coefficients can vanish. So the third root of 2, for example, is such a problem. And strange enough, when you think about the origami solution of this problem, it also transforms it, and it's convenient to transform it in the manner that you have here. Epsilon is 1 minus x, so you see the ratio. If you have a square and you fold up such that you make the standard folding operations to get the root, you see the ratio of 1 to the 1 to this the square root, the cubic root of 2 in this manner. So, the same is the Delian problem. This also a paper folding solution of this. Everybody knows that our Dean number is our Dean format number is 1 to square root of 2 of papers, but in the space to cut prism such that you get 2 prisms of the same side ratio would be the same of A to B to C is third root of 4 to third root of 2 to third root of 1. So you see this would occur again. And the n-dimensional prism format is about the same. It has to do with the nth root of 2. So this nth root of 2 is somehow impressive. How to generalize the golden mean? There are many ways to do it. So the first one was the cubic generalization of van der Laan and Rosenbusch, and I will talk about this a little bit later. And the metallic means of Vera Spinadel, she calls, if the quadratic equation is not x squared minus x minus 1 is 0, but x squared minus 2x minus 1 is 0. The solution is called the silver mean, and then you get the bronze mean and the copper mean and so on and so on. So all the metals are used up in there. Van der Laan and Rosenbusch both were architects, and they used these ratios, the solutions of their equations, to form rooms, furniture, and so on. And you see, we find Fibonacci type sequence to get those solutions. You see that the first solution is about 4/3, and the Kubi ratio of the German architect Rosenbusch is almost nearly 2/3. If you are in a room of this format, you wouldn't see the difference between the Kubi ratio and 2/3. And if you look at cars, who have heck door, which is not split in the middle, but in the ratio, in the golden ratio somehow, it's also 2/3, nearly the plastic number or the Kubi ratio. So it occurs in nature, in the technical nature too. So Fibonacci number sequence would be, in this sense, the typical one and the quadratic one, and the plastic number of van der Laan, you have to start with 3 starting values. Here it is, 3 start values, and it continues like this. And also here it's, of course, the way that the solution is independent of the start values. Dutch architect used this. And there is something quite similar to what we know from the golden rectangle. Starting what we have done already, I don't find the cursor, here it is. Starting with 1, again, and so on. And we find the golden rectangle, and we put it this way here. You see that the diagonal of 1 continued passes through this corner. So if you have the ladder problem, you would have difficulties to move this ladder along this walk. In space, you can do the same and get a van der Laan box or plastic box, because the number is called the plastic number. You got the plastic box. And plastic doesn't mean the material plastics. It means plastic to form 3-dimensional objects. Like in art, we also call a figure a plastic. Strange enough, if we have the thought to make the spiral a little bit better, not using quarter circles, but say quarter ellipses. If we take quarter ellipses, we have the possibility to increase the curvature while the circle curvature wouldn't increase in this part. So this is more similar to a logarithmic spiral, and we have the contact here is already a C3 continuous curve because the hyper-osculating circle is the same for both arcs. So, and if you calculate this is just the material of the gymnasium, we find the cubic equation finally. We have this cubic equation, and the short transformation of this cubic equation makes it to the Lamb condition. So it's related to this. But this is no wonder. We can, by a Tschirnhaus, bring Ferrat transformation, of course, transform cubic equations to whatever we want. And the same can be done with Rosenbusch. So, solving algebraic equations again of higher order. Find Fibonacci type sequels to a given sequel of coefficients A index I. The sequel is, of course, defined now by the degree, the number of consecutive Fibonacci type numbers is defined, of course, by n. You have to have n such consecutive numbers. And again, if you calculate the limit of this expression, you find that it is just p over x plus p2 over x squared, and so on. So we again find that the coefficients pj are minus aj by comparing the coefficients. If we have generalized this Fibonacci sequence, if this is convergent, we can calculate a real solution of this algebraic equation. Note if this generalized Fibonacci sequel is convergence, we have such a real solution, but we have to talk about the convergence criteria. We have to apply them. And if the equation has only one coefficient, we have to apply the inverse of the Tschirnhaus-Bring-Ferrat transformations. By this method, we do not get, of course, pairs of complex solutions. So if we have an equation of fourth order, we might have difficulties to solve it, but we can see directly it's not convergent, the sequel is not convergent. Then we have a criteria for that there are no solutions, there is no real solution. Needed are application of convergence criteria, and there we have to talk about mathematics again. You see, regular Weiss and Newton's method are far more general. They are applicable in any case, not only for algebraic equations. They are applicable in any case. Therefore, this topic is just more or less fun. The topic might be of interest for high school mathematics and informatics courses, and it involves somehow material which people should know. I think people should know about the golden section, they should know about the Fibonacci sequence, and how to generalize things. They are not closed. You can handle and generalize. Generalization is one of the strongest principles in mathematical research. Final remarks. The standard place of action is always the Euclidean geometry. Why? Because people in schools, when they attend the primary school, their world is Euclidean. There is a big difference between mathematics and geometry. Mathematics has 0 and 1, informatics too, 0 and 1. Geometry has no 1 and no 0. And this is a big problem, and this makes the difference. We have proportions. And if you talk about the Greeks only had proportions. They had proportions and the commensurability of numbers. This was a matter of proportions. So we talk about now visualization of mathematics. Visualizations means, on one hand, mapping of effect, and on the other, interpretation of, hopefully, this fact. So, by some viewer, or it's more or less a different persons who interprets it. And we want somehow that the viewer gets the same information as we put it in to the mapping. And the mapping is good if a naive viewer gets this, can guess the information. Somehow he must be schooled also. Criteria for mapping: simplicity, unique interpretation, and of course aesthetics. It should be a nice visualization. There are many hidden assumptions coming from the cultural background of the viewer and of the man or the woman who made the visualization. Standard place of action again is Euclidean geometry, and again geometry has proportions, not numbers. Geometry provides models for mathematical facts. Sometimes Euclidean geometry is not always the most clever place of action. For example, hyperbolic geometry might be better because it says more about the mathematical fact. And here we have it. Hyperbolic geometry, space-time geometry, geometry of metric spaces, we call them Minkowski spaces or Möbius geometry. They are logically better suited models to the mathematical facts. And here it comes. We talk about a plane, I mean the Gaussian plane, which in English literature often is called the imaginary plane or the complex plane. It's not a complex plane. The plane is real. So there are also different names for different objects. We are used to call it the Gaussian plane, and it's a real plane, which is a model for a real model for the complex one-dimensional numbers. And of course, we see that the sphere, the Riemannian sphere, I also found the word complex sphere for this Riemannian sphere is a model for the complex numbers. Now I have the problem. Okay, back. Mapping. So we have segments. Segments measured with Euclidean measurement. Historically, the golden mean is a ratio of segments. It's a one-dimensional thing. George Odom, American artist who finally get insane of geometry and mathematics, he found out when he took an equilateral triangle and did circumcircle, and he connects the midpoints, do I find the cursor? Here it is. The midpoints of two sides, and if he connects it and intersects it with the circle, he gets the golden ratio. So ratio, if we talk about a mathematical concept, is a concept invariant to affine transformation. Is this Euclidean figure really a good interpretation? No, it is not. It belongs to affine geometry, and you see if you make an affine transform of the left-hand side figure, you get an ellipse with a special a triangle with a any triangle with a special ellipse, circumellipse, and you find the golden section again here. So, what about the squares? The squares are a concept in Euclidean and affine. If you make some hard things, you can have squares in, let's say, Euclidean geometry. But if you live in a hyperbolic geometry, you don't have squares, you don't have similarities, but you still have Fibonacci numbers and the golden mean. So how to visualize it there? So you see, adding squares is not a good idea there. But what about circles? You may start with circles, with small circles in the middle, and turn around and just add to two former circles, one with a certain radius, the sum of the radii of the former ones. You can do this also in the Euclidean geometry and in non-Euclidean geometry. So this visualization would be much better, and it would deliver a new thing, a golden triangle, whatever this is, as a limit figure. So you see, this is a thing I am playing around, or thinking of the golden mean measures segments. You just need a metric space. Nobody talks about Euclidean orthogonality there. So a metric space would be enough. So we have metric planes, let's say Minkowski planes, and they are affine planes. There you could talk about squares also if you want to. You have a strictly convex, mostly smooth and strictly convex oval as the unit circle. And then you have circles, and you have quarter circles because it's centrally symmetric, and you can make this construction you made before also for this, and construct even bi-arc spirals in metric planes, which are not Euclidean, where you don't have a similarity, a full similarity rule, just centric similarities and translations. So with the group of central similarities and translations, it is possible to do something which looks like what we are used to see as spirals. Then, what about the dimension? Numbers are dimensionless. Segments are of dimension 1. So you visualize this number by segments, or in the golden rectangle by 2 dimensions. What about 3 dimensions? You can take a golden prism too, and it's in fact possible to make a spiral there also, which is a C1 continuous spiral consisting of helical arcs. A very, very nice object, which I think should be considered too. You can use also these Bézier splines or whatever. And so on and so on. I think I could show what can be done with very, very simple objects, and show to the pupils also and to the teachers that mathematics is not a closed thing, finished with the rules of, let's say, 2/5 and so on. It's a handling of equations. So to give them, the pupils, the feeling that mathematics is ongoing research should be more or less, should be more done in schools. So this ends my talk. Thank you very much.